Hello, everybody, and welcome back to the LPA seminars, today hosted again by LMU Munich. Today we are trying something new because this seminar is directly related to the upcoming workshop on machine learning and control systems in 2 weeks. So I hope that will kind of help us to set the mood. As usual, forgot to say that before, we're on YouTube, so you can post any questions at any time in the chat and I relay them to the speaker at the end of the talk, or otherwise you can join us after the talk. And so back to topic. Today's speaker is Professor Charlotte Palmer. She's a lecturer at Queen's University in Belfast. She did her PhD at Imperial and then did postdoctoral studies at DC, Lancaster, and Oxford. Currently, she's working a lot on high repetition rate laser-solid interactions, so we're pushing forward these experiments from single shot to something that can be measured in hertz. And she will be talking today about automation, optimization, and challenges regarding this. So Charlotte, it's a pleasure to have you here, and the floor is yours.
Thank you very much. And also you're a little bit too complimentary. I'm still Dr. Palmer. Also, I'd like to apologize if there's some background noise. Andreas is going to jump in because there is actually a man with a hedge trimmer right outside my window that hopefully won't disrupt the talk too much. So first of all, I'd like to say good afternoon and thank you so much to the team at Munich for inviting me to give this seminar. Today I'm going to be discussing sort of community progress towards high repetition rate laser solid experiments and in particular the generation of multi-hertz laser driven proton beams. Some recent experimental work that our team have been doing as well on automating these experiments. So before I begin, I'd like to acknowledge that team and thank them for turning these experiments into a reality. It's obviously not easy, so a lot of effort there. Okay, so the interaction of high intensity lasers with overcritical density targets provides a wealth of opportunities to explore physics ranging from sort of the fundamental light matter interactions to the production of bright radiation sources for different applications. And to just kind of illustrate that diversity in the physics that's involved, I'm going to describe a small subset that itself is including like a lot of very diverse science. And that is illustrated on the left-hand side over here. The interaction of a high intensity laser, so in this case, relativistically intense, with a micron scale foil. So this is a very common setup used for laser driven proton acceleration. At the front surface, we have the physics of the interaction of light and matter. So we've got a lot of processes contributing to the ionization and the heating of the subsequent plasma, which vary as the laser intensity increases, not just for different laser systems, but throughout the rising edge of the laser pulse. And this hot plasma also expands, and so it creates an environment that can support laser plasma instabilities, the formation and advection of magnetic fields, and even generation of shocks that propagate into the target. And so of particular interest for plasma accelerators is the generation of hot relativistic electron populations when the laser is sufficiently intense at this surface interaction. And those hot electrons can propagate beyond the direct interaction into the bulk of the target. So here, the population can derive a collision or return current, although it's sort of a relativistic and collisionless itself, and also the formation of strong magnetic fields, together with residual sort of lattice structure of this sort of cold, originally just cold and dense target. That can lead to filamentation of the electron beam and also of the internal currents. So there's a lot of stuff going on there. Typically, because these hot electrons have sort of MeV energies, they can propagate through the whole of a micron scale target and escape from the rear surface. And there they can set up a space charge field with the now net positive foil. And with that field being strong enough to ionize the surface atoms, which are often hydrocarbons if we don't take any special effort to cleaning the targets. And the resultant electron and ions that are born in these fields can gain energy from the fields, the electrons being accelerated into the net positive target, and the protons and heavier ions being accelerated away from the surface. So the absolute strength, the lateral extent along the surface, and the direction of the sheath field is depends on the laser parameters, and that's through the hot electron population. So the laser affects the hot electron population, which in turn affects the sheath field. And as a result, then that impacts onto the properties of the proton beam or heavier ions that are accelerating away from the target. So over the decades, experimental and theoretical work has allowed us to build up a picture of how these proton beam parameters relate to particular experimental control parameters. And in the grade box, you can see some of the proton beam properties and trends that have been determined specifically for target normal sheath accelerated proton beams, which is the sort of mechanism that I just described. So these are typically very beam-like beams with sharp gradients and flux at the edge of the beam. And you can see an example on the bottom left. So the dark gray is higher flux, and you can see it's dropping very sharply at the edge. They also have a very low emittance and a small virtual point source, which makes them very good for imaging or imprinting the sheath characteristics or the surface characteristics onto the beam. And you can again see in this image examples of lines that have been imprinted on the proton flux. They have a broad energy spectrum with sort of MEV temperatures and a divergence that decreases as the proton energy increases. So it's a narrowing at higher energies, with a cutoff energy that's sort of tens of MeV, although there's been more advanced sort of schemes recently that tailor the laser or the target parameters and achieving 100 MeV scales of energies. So these characteristics and their variations with the experimental control parameters, so the target and the laser properties, make laser-driven proton beams an interesting prospect for a wide variety of applications. But the variability, which is also accompanied by high shot-to-shot fluctuations in these beam parameters, is sort of indicative of the complexity and the nonlinearity of the parameter space where the acceleration is occurring. So if we have sort of small changes in our interaction, then we're seeing significant changes in the output beam properties. And while that provides us with sort of powerful mechanisms to tune this beam, it also provides challenges for long-term beam stability. So as an example, maximum proton energy is generally seen to increase with increasing laser intensity due to the fact that we have higher electron temperatures. So there are a number of hot electron temperature scalings that have been derived theoretically or empirically, which perform very well with experimental data. These models typically include the laser intensity, but they also include other factors. So maybe sort of the contrast or the pre-plasma scale length. And as more experiments are performed, more factors sort of need to be included to modify these models so that they appropriately fit the experiment and where it was performed in parameter space. A recent example is this paper from Dover et al., which published a refined model which takes into account the size of the laser focus. So this work indicates that to achieve the electron temperatures that you might expect from the theoretical models like the ponderomotive scaling, the high intensity region needs to extend laterally with a certain extent. So in that sense, trying to strive to higher and higher proton energies by just more tightly focusing the laser to achieve higher laser intensities might not be the optimum path. Similarly, there have been several studies recently that explore the effect of tweaking the laser temporal profile and the distribution of frequencies within the laser pulse. So these adjustments away from best compression and highest intensity have also shown a significant effect on the maximum proton energy, and which is still not fully understood, but it's really interesting work. So I would point you towards these papers. All of these factors act to make the characteristics of laser-driven proton beams challenging to predict. And in order to control and tune these beams for applications, we need robust models of the parameter space. And to build those models and understand the uncertainties that we have and how those also vary across parameter space, we need a lot of data. So very fortunately, in recent years, there's been a huge increase in the number of high repetition rate laser facilities that offer this multi-hertz operation, and also laser energies that are of the hundreds of millijoules to multiple joules, which are suitable for trying to produce bright secondary sources. So I've included just a very small set of examples here from around the world that are either systems that are already operating or soon to be operating. And these will enable experiments to move from hundreds of shots to thousands, tens of thousands of shots, or even more. But high repetition rate lasers are only part of our journey towards more data. So we also need our targets to be replenished at the same rate. And this is because every time we have a laser shot, our sort of solid target is destroyed. So traditionally, laser solid experiments have used a really wide range of target types, but thin foils are by far the most common, in particular if you're looking at the production of proton beams in the manner that I described. An important characteristic of all of these targets is that they are accurately placed in relation to the focus. This is because in order to achieve these high proton energies, the lasers are typically very sharply focused to only a few micron spot size. And that means that as a result, we also have a very short Rayleigh length, which is the length over which the laser intensity stays very high. So it's often on the order of 10 microns or less. So targets therefore need to be positioned with sort of micron scale precision. There's been a lot of work in the community over the recent years developing quite a wide array of pretty exciting targets that are also compatible with high repetition rate or Hertz repetition rate. And I've posted a small subset here with some references for further exploration. The developments include sort of tape drive style targets that are probably the closest to the traditional foils. And there's an example of one in the middle here. So these provide quite easily several micron thick target foils, but there are also novel etched foils that can achieve reduced 100 nanometer thicknesses or microstructured tapes that can get to higher proton energies. So thinner targets are more beneficial for higher proton energies. But obviously that's a little bit more complicated than just using a regular micron foil. Another issue is that tapes can produce a lot of debris, or we see a lot of debris from solid targets, and particularly when you then start running solid, these foils can end up sort of coating the vacuum chamber. So debris is an issue, and using these, you need to couple them with some kind of debris mitigation. There's also a whole suite of low debris targets that have been developed, which include sort of gaseous clusters or even having blast wave shaped gas sheets, using liquid or cryogenic droplets or ribbons or cylinder targets. And together with liquid sheet targets, which you can see pictured on the right and that provide kilohertz compatible operation. These more novel targets, they've been less explored, and there are some associated challenges with them, which in particular are sort of synchronization of small targets like droplet targets with equally small laser focus that you're trying to make sure that they meet at the right point. But also compatibility with vacuum conditions. So the liquid sheets or trying to operate cryogenic systems and making sure that you can maintain a nice vacuum that you need for your laser propagation and also for your diagnostics. But despite these sort of technical challenges, the targets have been used more and more recently, and there have been some really nice results, and they're becoming much more robust and stable. And so there's really promising work for the next years. So these developments in target technology have also been accompanied by similar developments in diagnostics and detectors. For studying laser-produced proton beams, the field's traditionally relied on quite low repetition rate or intrinsically low repetition rate detectors like dosimetric film stacks that need to be scanned after exposure. So while these diagnostics provide the advantage that they simultaneously give us high spatial resolution transversely across the beam and energy resolution by using some kind of stacked geometry where protons of different energies penetrate different depths into the stack, they just can't really be used for large volumes of data. So scintillators coupled to cameras have been explored as a way of trying to sort of closely mimic this setup and simultaneously getting spatial and energy resolution by providing the energy resolution through either varying the scintillator emission wavelengths and trying to avoid crosstalk between the scintillators, using geometries where you can sort of access each scintillator in the stack to image them separately, or by including sort of filters over the top of the scintillator so that with one scintillator you have access to many different energies through the propagation through different thickness filters. So there's different bands. Alternatively, you've got direct detectors. So they're also being explored, like the radii large CMOS chips, where the particles are incident sort of directly onto the chip, or diodes. So in the bottom here, we've got a time of flight diode. Now, although the source of the protons is comparable to the laser pulse duration in duration of the source proton pulse, because they're non-relativistic, dispersion of this broadband beam as it propagates over some distance means that by the time it reaches your detector, you can have sort of the energy mapped into nanosecond timescales that are easier to read out electronically. And so the time of flight detector can provide you with a point measurement of that energy spectrum, but they're also being combined as mosaics to give sort of spatial resolution or layered to provide extra information. So by combining all of these together, the high repetition rate lasers, targets, and diagnostics, we can get more data. And again, just looking at a couple of examples, because there's been a lot of work on this, we can see what that can then give us. So in the top row, you've got tens of shots that are taken using tape drives or tape drive targets. And these sort of demonstrate either the stability of the proton spectrum, but also how you can then use those multiple shots to determine an average spectrum and get some sort of statistically derived measurements of the fluctuation and sort of the variability of this spectrum. In the lower plot, these are kilohertz lower energy systems that have been used to scan the variation in parameters, so using sort of a fine scan through parameter space. On the right, these are electron and proton spectra from hundreds of nanometer thick water sheets. And these show the variation in also electrons reaching higher energy as we go through focus, which is the vertical axis, and a dip in the proton spectrum at best focus. Then on the left, we have front surface accelerated protons from a spinning disk target. And this is showing the variation with a pre-plasma scale length created by an external pre-pulse. So together, all of these systems allow us to gain more data than we could ever have had before. And in order to deal with that, we need to think about the way that we gather and interact with that data. So the last decade has seen the proliferation of machine learning techniques due to the rapidly increasing availability of data and computer processing power. These techniques have been adopted by a large number of research disciplines where they've addressed problems that are often unresolvable in reasonable timescales by any other methods. The plasma and accelerator communities have already adopted these tools. A very common category is for diagnostic analysis, so like fancy fitting. In particular, if you've got problems or inverse problems with many parameters. In this example from Livermore, a neural network has been trained to rapidly analyze and retrieve the proton beam characteristics from a filtered scintillator like the ones that I was talking about earlier. So this takes into account complexities of the beam, such as the divergence of the proton beam and how shadowing sort of affects the retrieved spectral and spatial information. As well as the analysis of diagnostics, machine learning tools can be used to determine complex correlations between multiple parameters, and by doing that, to create synthetic diagnostics. So the example on the left is from an FEL, and here the longitudinal phase space of the electron beam is really important. But direct diagnostic techniques like transverse deflecting structures are destructive. And so here, Emma et al. At SLAC combined measurements from their destructive transverse deflecting structure with non-destructive diagnostics like current and coherent radiation monitors, and they use that to train a neural network. So then the neural network learned to relate the longitudinal phase space to the non-destructive measurements, and it could demonstrate good predictions of what it thought the TDS should look like based on the non-destructive diagnostics alone. So a way of providing a measure of the pulse shape without actually having to destroy it. A similar technique was used by Meyer et al. To train a model to predict the properties of a laser plasma accelerated electron beam using the laser parameters. Here you can see the prediction of electron energy showing a sub-percent level agreement with the measured energy over a 24-hour period. So another powerful tool from the machine learning sort of repertoire of tools is finding optima within multidimensional parameter space. Using automated optimization in comparison to having an expert operator who's been trained up over many, many hours can provide much more consistent operational results, and is also much easier. You know, the machine doesn't get sick or take days off, unlike an expert operator. So this example here is from Chalou et al., who demonstrated optimization of X-rays generated from a laser-driven plasma wakefield. And then the algorithm tuned the laser and the target parameters in order to increase the measured X-ray signal. So here you can see the measured X-ray counts in the plot as the X-ray counts. And you can see with each shot how the signal increases as they're varying the laser pulse shape, the gas cell length, and the density. And on the right, you can see the signal moving from just sort of noise at the initial conditions to being optimized to a bright signal where the filters in the beam are clearly visible. So this machine learning optimization utilized Bayesian optimization with Gaussian process regression. So this choice is due to the nature of the problem, and it's also been used by other groups with some references down in the left. So the reason that we're using that is typically in laser plasma experiments, we're trying to find an optimum from noisy measurements. But we're also keen to not just find some kind of optimum point, but to learn about our parameter space. And also to have an idea of the confidence that we should have in any model of parameter space that we build. An additional challenge on top of that is that our data isn't cheap. Each new piece requires a new laser shot. And so we want to make sure that we're using a system to build this model that's not wasteful, that incorporates all of the data. So these sort of criteria led that group towards Bayesian optimization using Gaussian process regression, which does incorporate all of the data into the model that it's building, and it tracks the uncertainties. In our experiment, we used the same control and optimization system used for the Chalou paper, and so I'll outline that a little bit more here. Matt very kindly provided these nice graphics to explain the different steps of the optimizer. And so first of all, we have this example parameter space where here it's just a function of one variable. So then we sort of measured some data which is randomly distributed points on the function. And now at the moment, there's a whole world of functions that could fit through these points. And this is increased by the fact that these data points are noisy, and so they're not 100% certain, they're not 100% trustworthy themselves. So the algorithm takes those possible functions and it determines sort of a mean function and a distribution of sort of possible functions that could fit with those data points. There's also a certain expectation of smoothness, and so that's why it doesn't just sort of massively blow up these errors in between the data points that we know, because it's expecting to have a function with some kind of smoothness, some scale. So now it sort of decides where might be a good point to take some more data and where we might find higher signal than we have previously measured. And here it's sort of saying there's a good expectation on either side of this high point that we'll find something better. So it picks one of those points and takes some data. And you can see in this case, it was higher. But it's not just taken a single piece of data, it's taken enough data at that point to be able to build up also a measure of the fluctuations in the data at that point. And then it's picking a new position for a possible more optimum shot. So then it gathers more data and the same process goes on again until eventually sort of constrains the model pretty well around this optimum here. You can see that the uncertainty sort of dropped down. And so then the model can explore further and just see if there are other optima. And if you look here back at the Chalou plot, you might see that towards the end, we see the data points as actually kind of dropping down in the number of X-ray counts per burst. But this red line, which represents the predicted optimum, is staying high. So we're just kind of exploring the parameter space more and dropping down the uncertainties, but not finding a better optimum. So our experiment was performed at the Gemini TA2 laser facility. So actually even the same laser facility at the Central Laser Facility in the UK. TA2 is a joule-class Ti-sapphire laser, which can deliver 5 Hertz pulses to TA2. And here you can see a Sequoia measurement of the picosecond pulse contrast, which indicates that we had around about 10 to the minus 8, 10 to the minus 9 contrast with a pre-pulse at around about 65 picoseconds before the main pulse. The compressed pulse had a duration of just under 40 femtoseconds at best compression and contained a few hundred millijoules. We focused it with a 90-degree off-axis parabola that was an f2.5. So we achieved a few micron spot size that you can see the measured and the Gaussian fit on the right, and intensities in the mid 10 to the 19 watts per centimeter squared. So our corresponding Rayleigh range, where we had a high intensity region, is approximately 10 microns sort of either side of focus. In order to monitor and control our system, we've got sort of sets of standard diagnostics and optical elements along the path. So here you can see a kind of simplified cartoon where our stretched amplified pulse enters from the bottom right. And we use leakage diagnostics to monitor the long-term contrast and then near field and far field cameras here. These are cross-calibrated with power meters to give us an idea of the pre-compression energy, which can be controlled through a motorized wave plate that's before the room. After compression, we also have a pick-off through a thin window and to a spider diagnostic to get the temporal profile of the beam. And then we have an adaptive optic in this chamber to control the wavefront, with another set of leakage diagnostics that provide on-shot measurements of the wavefront, the laser pointing, and also a post-compression energy measurement, so for any losses in the compressor. Oh, I guess I should go back. After that, it does go into the main chamber, and then we have a relatively simple beam path that just goes through 2 wave plates to give us control over polarization, and then focus down onto the target here. The target that we used was for most of the experiment was a tape drive developed at Imperial College in London by Nuo. So the tape drive has 2 very easily replaceable spools that can be customized to support different tape widths and can hold several thousand shots worth of tape. It was mounted on a custom support so that we had as much diagnostic access to the rear surface as possible. And also we could adjust the tension so that we had different materials or target thicknesses. We predominantly use Kapton with sort of 12.7 or 50 micron thickness, but there was also some copper and some steel tape available, so we did some tests with those towards the end of the experiment. This tape drive was then placed on an encoded XYZ stage using a kinematic base so that it was easy to kind of take out and swap the spools. The tape drive itself had micron scale positional stability, and we measured that using a commercial white light position measurement system. So this crocodile system, and you can see the measurements here along the bottom. Despite that stability, we did notice that we saw occasional jumps in the position of greater than 10 microns, which is, a problem for us if that's our Rayleigh range. And while it wasn't possible for us to determine the cause of those jumps, we were able to monitor the surface position on shot using self-emission imaging along the normal to the laser propagation direction. So here you can see kind of a cartoon of how that was set up, and also the calibration that was used to relate the laser position to the target stage. Now, to accommodate the jumps, which lead to an offset of this calibrated position relative to the stage, we used a weighting of the previous shots so that could then be applied and ensure that the calibration remained in sync with the tape position and the data was appropriately placed in parameter space. For the last few days of the experiment, we also tested a water sheet target provided by Siegfried Glenzer's group at SLAC. And so that can provide millimeter scale liquid sheets with variable thickness down to hundreds of nanometers, very similar to the Ohio sheet. Around the target, we had a suite of diagnostics, including measurements of the reflected laser light with a scatter screen at 1 and 2 omega. So you can see a color image of the interaction on the left-hand side with the scatter screen sort of glowing pink. And also with these plumes of glowing material coming from the front surface and the rear surface of the target, with this pellicle before the parabola providing protection. So this is our sort of debris shield. We also had a reflective probe from the rear surface and a complement of particle diagnostics, including electron spectrometer, 2 time-of-flight diodes, an active Thomson parabola, and a proton scintillator. So the proton scintillator that we were using to measure the spatial profile of the proton beam utilized an inorganic scintillator, which is so EJ440 specifically. And this scintillator has a very well-matched thickness to its scintillation layer in comparison to the proton Bragg peak, so that the signal's dominated by the stopping protons rather than by electron or X-ray background propagating through the scintillator. In order to confirm that the signal was due to protons, we included 2 strips of aluminium foil onto the scintillator and looked at the drop-off in signal behind those shielded regions. And so you can see a photo of the filter here, or the scintillator with the filters on here, and then an image of the exposed scintillator on the right. You also see there's an imprint of an 8 micron copper mesh that was included behind the target for a few runs. Dose calibration is ongoing with comparison to some RCF and also to Nick's trying to book some time at a cyclotron. If you look up here, we also have this slot cut in the scintillator, and that was to provide line of sight to the rear surface or to further back diagnostics. So along this yellow star, that's the target normal direction that goes on to the Thomson parabola, and then the blue star goes to the rear surface time of flight diode. So these were both of these diagnostics were intended to look at the proton beam energy. The first, the active Thomson parabola, is being developed at RAL. And this uses a phosphor screen as a detector that's coupled to an Andor camera. It actually uses an enormous fiber bundle to transmit the imaging, but wasn't really necessary for TA2, more for higher energy systems. Due to the space constraints, though, inside the target chamber, we did have to have the active Thomson in an external chamber out of the back, So it was more than a meter away from the target. And as a result, we had to have quite a large pinhole to ensure that we would get enough signal. And this meant that really the proton trace is the only one that we could clearly resolve. And you can see the data in the bottom right, where we've got a proton trace, a 0 point, and then a sort of general heavy ion smush. So we think there were heavy ions, but it's going to be more of a challenge to see if we can, what information we could get out of them. Much closer to the interaction, we were able to place a time of flight diode at a few degrees from the target normal. These were diamond diodes provided by Daniele Margaroni, and they were coupled to a 5 gigahertz Acroy scope using low noise cables. You can sort of see a very dark picture of the time of flight diode here, where it's illuminated by the greeny laser going through the mesh behind the target. And I've included an example trace in the bottom right, showing a relatively weak photopeak and then the rising edge of the proton signal, which we could use to determine the peak energy. And so finally, we also used a central laser facility electron spectrometer, which is kind of a completely enclosed unit in a little lead box with the camera inside and networked. Our screen detector that we used was a Lanix, and a small 150 millitesla magnet here, so just all contained within one nice little unit. The raw data, you can see an example of it here to the left. So the tiny magnets don't have the most amazing fields, so we do have this sort of unusual structure to the E-spec. We had kind of a low energy cutoff of 750 and around about up to about 15 MeV. There's reasonable dispersion to see. So to enable the experiment to run in automated fashion, we utilized the control system. So this is an extension of the one that was used for the earlier experiments. And in the cartoon, you can see how it interacted with the different pieces of hardware within the laser system to provide control over the wavefront, the temporal shape, the energy, and the polarization. And machine safety was considered through having specific bounds to prevent the control system from moving the laser into potentially dangerous areas. So where a lot of laser energy would be clipped by the dazzler and sort of just dumped. We also had control over a variety of motorized stages. And that system meant that we could perform a variety of scans. So say a focus scan, either using motorized stages or the adaptive optic. And on the left at the bottom, you can see an example of a target Z scan, where at each position, there are a burst of shots, and the average pixel value from the 2D image of, say, the electron spectrometer is used to create a value for that shot, so an average pixel count. Then we have a burst of shots at the same point, which gives us a standard error. And so we can see how that average and the standard error changes across the scan. That can be repeated very easily at multiple points through the day. And we used it to just sort of monitor the stability of the setup. The automation coupled with the simple online plotting, so like those 1D maps that I just showed, and a live data display that we had sort of up on the wall that just showed us all the raw data, enabled us to exploit the laser repetition rate and also quickly identify any issues that needed to be fixed or areas of interest. And so that meant that over the course of the experiment, we were able to acquire close to 100,000 shots. And you can see the number of shots per day here on the left, and then also the accumulated data by one specific diagnostic, so the proton scintillator on the right, with the big gap for the asbestos removal, laser maintenance, and we use that also to change our target. Control over the laser energy using the wave plate allowed us to sort of start each day with a bit of an energy scan, so that check everything's all right before you just immediately blast it with full energy. And so here you can see some of the plots that either used average pixel count like we had before, or for the proton energy, the rising edge of the time of flight signal to provide a maximum proton energy. Runs 3 and 5 are just the same. They're energy scans, but from consecutive days using the 50 micron tape. As we might expect, the reflected laser energy in the first and second harmonic, which is shown here in the upper right, increases with increasing laser energy, as does the electron spectrometer flux and the proton flux taken from the proton scintillator. But you might see that there's kind of a bit of an offset here, that the proton flux doesn't start going up until we're a bit more than halfway through scanning up the laser energy. And also that it's very, very confidently zero, right? You know, that there's no sort of error bars on these points. So that's something that I'll come back to in a bit. And it's an indication of sort of the threshold behavior that we were seeing with this diagnostic. As well as the increase in flux, the TOF also shows us that we have increasing proton energy with increasing laser energy, as you know, we would hope. We typically had a few MeV beam energies, and these protons from the target tape were smooth. You can see an example on the left-hand side, and hopefully, yeah, that'll do something. And some 2D Gaussian fits that were used to analyze this data, give us divergences of 10 degrees and fluctuations in the centroid position of a few degrees. We see a reduction in the divergence for the water target, and we're currently exploring potential drivers for that. In the top right, you can see the mesh overlaid in red from different shots in a run. It's a bit like psychedelic when they're all going at the same time. So you can see how the mesh is sort of moving around a little bit from shot to shot. So this jitter corresponds to about 1 to 2 microns shift at the target plane, which is comparable with our focal spot and its jitter. The proton flux is very dependent, as we would expect, on position relative to the laser focus. And here in the bottom right, you can see burst average images as we scan through the laser focus. So this is one side of focus, and then we're kind of reading left to right and down to the bottom to the other side of focus. And so you see that the burst average flux kind of increases, but then it dips on the in the center, which is where we have our peak intensity, and then again it drops down the other side of focus. This is was visible through most of our experiment, although the dip varied in extremity, you know, like how visible it was through the experiment, but it can be much more clearly kind of seen here than in those 2D plots. And you can also see that, well, here's just a repeat of 3 runs taken on the same day and overlaid with one another. And that's over a sort of 150 micron spread. Yeah. So you can also see from the time of flight measurements that there's a corresponding dip in the proton energy. So that's consistent with what the kilohertz water target was showing in Ohio in those original sort of examples that I showed. And we see a corresponding dip in the conversion efficiency into the second harmonic in the bottom left here, and no sort of real effect on the electron spectrometer flux. So as in Ohio, we believe that these dips are due to the relatively poor contrast of the laser, leading to target disruption when we have the really the high intensity pulse, and consequently also high intensity pre-pulse. So as well as 1D scans, the system also supports multi-dimensional scans. And here you can see the average counts. So these are all different diagnostics. And then this is a scan of astigmatism versus target position, where each of these points are 15 shots at the same location in parameter space. And so as you might expect, we see a strong maximum for the electron signal where we have best intensity. And for the protons, as we have seen, have a dip at best focus with some peaks on either side. So in comparison, there's some 1D maps on the right-hand side. So these are for the electrons, which do target Z or astigmatism. And you can see just how much more insight, I guess, you get from the 2D maps of sort of how these 2 parameters relate. As far as the control code is concerned, you could grid scan an arbitrary number of parameters, but this scan took around about 50 minutes. And so if you wanted to add in an extra dimension, you could easily be up to like many hours. And a lot of this space is just 0. So an alternative is using an optimization to sort of intelligently sample the parameter space. So the optimization is factored into the control system using those kind of quick, robust analysis that I've already demonstrated, so like the average of an image. And it's factored in through the optimizer to then take control of the system. So you'll also notice that the target position is fed into the machine learning algorithm. This has a very, very strong effect on our output parameters. And so it was important to have it included in basically all of our optimizations. So here you can see again an example of the electron spectrometer signal. And like we did before, we would take many of these at a single location, then take, say, the average value and see how that varies between the different shots, and plug that in as some kind of a fitness value to the algorithm and say, we would like to maximize this number so that we'd try and increase the flux. So originally it would take sort of some random samples and then try and map the parameter space. So on the right, you can see the output from a simple optimization, just using the same two parameters as the 2D scan. And this is astigmatism and target Z again. And the optimization was started just away from the best, where you can see this red star. At first, it's sort of rapidly kind of like improves, and then it stagnates. And this we found pretty suspicious because there's a lot of really nice data points up here, but the model just doesn't seem to believe them. And so it was around about this point when we started to question the effectiveness of using the target stage readout as the target Z position input into the model. And so if the stage is not moving back, or the target is not at exactly the same position that it thinks it should be, then that will have a lot of effect on the model, and it will cause it to lose confidence in some of the points that it's found. You know, if it goes back to a very similar location, but now it gets something rubbish when before it had a good signal, or very close to where it had a signal before, you know, it's expecting that the parameter space has some kind of smoothness. And so that kind of confuses the model a bit. So by incorporating the measured target positions, we're able to get much better prediction, as you can see in the lower plot. So the predicted optimum condition here, the black star, is much closer to sort of the center rather than the orange star, which is way over here. So this sort of highlights the importance of providing the optimization with accurate information. And as we modified our code to utilize the measured position, we could do the same thing with other on-shot parameters, so like pulse shape or wavefront, to ensure that any kind of optimization or model builder is really using the most accurate information. Another challenge that we faced during the optimization was that some of the fitness values for the diagnostics exhibited this sort of threshold behavior. So effectively, we would have a signal. When we have a signal, we take several measurements, and the fitness value jiggles around a little bit. So we have these error bars. But if we fall below the noise floor, then we just get the same value every time. 0 is 0, and it's very confidently 0 with no error. And so in this case, this was coupled with the fact that our search parameters were also too large. So we would start at a point where we were pretty confident that we would have some signal, and then the model takes its sort of 5 random search points, and then these would be too far away. So it would be getting 0. By that point, we were in bad regions of parameter space in our random search. And it would be really confident about those. And so that kind of led it to doubt that we kind of had ever had any good signal anywhere in our parameter space, and the model collapsed. So by adjusting the search parameters so that initially, we were pretty confident, like if we're at best focus, we should get some signal. So if we have our random points initially distributed closer to that on a smaller scale, then we were more likely to get some signal. And also by adding noise to these kind of 0 points, ensured that they had sort of less pull over the model optimum, and mitigated the collapse. I'm nearly there. So over the course of the experiment, we performed a number of optimizations, and the ones I've kind of shown so far are quite limited in terms of the number of parameter spaces they explored. But we also used the code to explore a larger number of parameters. So here you can see particularly this is optimizing the adaptive optics. So the target position as always, and then the different Zernike modes. So we've got the spherical coma, different parameters of the wavefront to try and improve the maximum energy recorded by the time of flight diode. So in this case, this 5-parameter optimization shows a better than 2 times increase over where we were originally at best focus. And in this case, it was actually very rapid. I think that's just luck in our initial sort of the first 5 points are kind of randomly selected. And it just happened to find something really good straight away. But it gives an example of how the model can optimize. And also, in this sense, it was robustly exploring the parameter space. So you can see in this pair plot on the right-hand side, the different parameters that were being optimized and where the different data points that they took in parameter space. So we're sort of nicely distributed over the range of parameters. And you can see that for most of them, there's not a strong correlation between the fitness values and that parameter, whereas this plot here in the bottom right shows how fitness varies with Z. And there's a very strong correlation, you know, so in this case, our target Z position is really the thing that is sort of driving the optimization. If this is off, then the beam is going to be bad no matter what we do with the other parameters. And so high intensity laser solid interactions can be used to study a wide range of phenomena and as a source for secondary radiation as well. The community's achieved loads in recent years and developing targets and diagnostic technology to support a shift to higher data acquisition rates with the goal of improving understanding and also controlling the interaction. And Bayesian optimization using Gaussian process regression is a very suitable method for optimizing noisy data that's costly to obtain and providing both a map of the parameter space and an idea of the uncertainty on that model. So we've implemented an existing optimizer and developed it to work with a joule-class laser solid experiment. We've got a lot of data that we're still sort of actively exploring. It's still sort of the early stages and working out all the calibrations with the goal of developing it in such a way that we can kind of make it accessible to the community, both the data and the metadata that can then help to support the development of new tools. Before I close, I just want to highlight, as Andreas was saying, that in just over a week's time, there's going to be this control systems and machine learning workshop that's associated with this seminar series. And so do register. And also linked to that, there's a special issue of the High Power Laser Science and Engineering Journal that's looking at sort of the future of control systems and machine learning in high power laser facilities. And that's currently open. So do consider submitting something. Final plug is, so women and gender minorities, non-binary people are underrepresented within artificial intelligence and machine learning. And I've sort of been helping out with this charity that was set up by Oxford computer scientists to help try to reduce those barriers. So they provide a free introductory, so they've got free introductory course material that could be used to run courses. So if anyone is interested in learning a little bit more or hosting a course at their own facility or institute, then do kind of let me know, and then I can share some information. And I just want to say thank you all to my collaborators and also to you for your attention and your patience. I've been a bit long, sorry.
Yeah, thank you very much, Charlotte, for this great talk. It was really nice overview, and then the experimental results are very exciting. It's like really big data sets now. It's gone far away from those single shot measurements. I have one question regarding the results you showed and regarding the crocodile correction. is that something that you apply to like every single shot that you do, or is it something that you do on the mean measurement? And so in general, then to put this question a bit broader then, there are these two different approaches currently to Bayesian optimization, this stuff that Matt has been doing, where you say, I average over a lot of shots and then I take kind of mean value, or what Sören Jallas did at DESI, where he measures a lot of things and puts every single shot in the model. So what did you do here?
Yeah, so I think with the optimization, we were using the mean values, and also I think with the Z correction. So the way that the Z correction was working is it was sort of, I guess, almost like a separate model, right? That we had this this calibration, but that there would be some potential shift. Now, normally there wasn't really a change and the calibration would hold, but it was just that sort of every so often, and this is not on a shot-to-shot basis, but more like kind of every 10 minutes or something, there would just be a random jump. And so we wanted to make sure that then wasn't, or what we saw was that was disrupting the optimizations, and they just weren't being able to optimize anything. So I think that the self-emission diagnostic was captured on every shot, and I would have to check again whether the model of the Z position was really being updated on a single shot basis, or whether it was being updated after a burst of shots. I have a feeling it was probably a burst of shots, and then because the change wasn't typically so rapid.
And what would be the burst size that you use typically in these experiments?
So we varied, but we kind of settled in the end on probably around about 20, between 10 and 20 shots per burst. So the 2D map that I showed you, we previously did one with 5 shots per burst, and we saw some, actually, if I kind of like, I don't think that I put it in any extra slides, but in our 2D map with 5 shots, we saw something similar, but we sort of, the peaks were perhaps less defined. And so when we saw one of these sort of bright pixels away from the best focus for the proton spectrometer, or the proton scintillator, we thought that maybe it was just noise, that we'd had kind of one randomly bright shot had sort of changed things. And so that's why we repeated it with the 15 shots. So I think because there was still quite a lot of shot-to-shot fluctuation, that's something that we want to look into. Having more shots was definitely better. It gave us a more appropriate average, and also helped with the standard error. But yeah, I think we'd be quite keen to looking at the individual shots. So we have the capability of matching the shots so that we can do things on a single shot basis, kind of retrospectively.
And so one typical Bayesian run is like 100 bursts or something, order of magnitude then? So
yeah, so I guess maybe this is not so great, but it depended on how good it was, right? So this was 7 bursts, and then we stopped. This was going nowhere. But we did do typically around about, say, sort of 60, 70, kind of like 80 bursts, unless something went really wrong at the beginning, and then then we would kind of cut it off a little bit soon. But if it looked like there was something happening, then we just kind of let it go until there wasn't so much change anymore, or the time had just gone too long.
Yeah, so you mentioned timer, because I was just estimating that would mean like one scan is typically like 2 minutes, I think, if I calculate correctly.
Yeah, because there's also a little pause between the bursts. We have, I think we're doing sort of 5 seconds something between the bursts.
Okay, because I was wondering, like, if you like do one optimization run, and if you ever like repeated the same thing like half an hour later and noticed that something had shifted or so, because with the averaging over like 10 shots, you get like average over like quick fluctuations.
Mm-hmm.
But then there might be something which is slowly drifting as.
Yeah, so we did notice, well, we did not so many, we did do a few kind of like repeat optimizations, but we haven't really looked into kind of comparing them as a time evolution yet. It was more, normally we were fixing and rerunning the optimizations, but we have got a lot of repeat scans of single parameters from throughout the day. And so by looking at those, we noticed that there's not too much of a change, except for when something was happening. Like there were a few days where there were problems with the laser and one of the pumps would drop out. So we wouldn't necessarily immediately kind of notice it, but there would be a shift in the focus. The best focus would have been kind of translated by hundreds of microns. And so that, because it was normally so consistent, if we rerun a Z-scan, then it's kind of overlaid nicely with the Z-scan from earlier in the day, that when it was shifted, then that was something that really pointed us to something's gone wrong back in the laser chain, or there's something we've missed on one of these screens that's changed.
Yeah, that's very interesting. So I haven't gotten any questions yet from the Zoom. I would suggest that we just invite people quickly over. I know you can't stick around for long, but we will have plenty of time to discuss at the workshop in 2 weeks' time. Mm-hmm. And before I close, I would like to quickly advertise next week's seminar. So first, on Tuesday, Daniel Seibt is going to talk about the effect of laser polarization on electron pointing jitter in LWFA. And then on Friday, there's a second warm-up talk by Peter Hatfield on the data-driven future of high-energy density physics. So be sure to tune in again. And until then, have a nice weekend.